Welcome students once again into the class of number theory, and in this video we will proceed further on the chapter of quadratic residues by defining Ligander symbol and then looking at some properties of Ligander symbol and to check whether A is a quadratic residue of P or not using Ligander symbol. So let us see what is Ligander symbol is. So first of all, write down Ligander symbol. If P is a prime and A is any integer such that GCD of A and P is 1, then Ligander symbol is denoted and defined as so we denote Ligander symbol as A by P within this round brackets, and the value of this Ligander symbol, and we will read it as Ligander symbol A by P. So Ligander symbol A by P is equal to 1 if A is quadratic residue modulo P, and is equal to -1 if A is quadratic non-residue modulo P. So this is the definition of Ligander symbol. One thing that we know very well, that A raised to the power P minus 1 by 2 is congruent to 1 if A is quadratic residue modulo P, and is congruent to -1 if A is quadratic non-residue modulo P. So looking at these two, comparing these two, it can be visualized very easily that they are same. Ligander symbol A upon P, A by P, is equal to, or you can say is congruent to, A raised to the power P minus 1 by 2 modulo P. So you can have this, that Ligander symbol A upon P is congruent to A raised to the power P minus 1 by 2 modulo P. It is a straightforward result and is known as Euler's criteria. So it is Euler's criteria that says that the value of the Ligander symbol A by P is equal to A raised to the power P minus 1 by 2. In fact, it is congruent to A raised to the power P minus 1 by 2 modulo P, because otherwise it will have values other than 1 and -1, whereas A by P Ligander symbol can assume only those values which are 1 and -1. So it is congruent to, it is not actually equal to, it is congruent to A raised to the power P minus 1 by 2 modulo P. When you will solve it by taking the residues after dividing by P, you will get either 1 here or -1. If A is a quadratic residue of P, then you will get 1 here, and if A is a quadratic non-residue modulo P, you will get -1 here. And this definition will obviously be satisfied that A upon P is equal to 1 if A is a quadratic residue modulo P, and -1 if A is a quadratic non-residue modulo P. So this is the definition of Ligander symbol, and simultaneously we have seen the result of Euler's criteria regarding Ligander symbol. Now we will have very easy, very simple theorems. I'll write them at once and then prove one by one. So statement of the theorem is, if P is an odd prime and AB belonging to Z be such that GCD of A and P is 1, GCD of B and P is also 1, then there are several results regarding Ligander symbol which we will prove. Then number one, AB upon P Ligander symbol is equal to Ligander symbol A by P into Ligander symbol B by P. This is the first result we will prove. And I'll prove them one by one. I'll write the next one after that, and then I'll prove that, and so on. So here we are to prove that the Ligander symbol AB by P is equal to Ligander symbol A by P into Ligander symbol B by P. Look at Ligander symbol AB upon P. By using Euler's criterion, it is congruent to AB raised to the power P minus 1 by 2 modulo P. Now AB power P minus 1 by 2 can be broken as A raised to the power P minus 1 by 2 into B raised to the power P minus 1 by 2 modulo P. Once again, it is congruent to. Using Euler's criteria, this A raised to the power P minus 1 by 2 modulo P is congruent to the Ligander symbol A upon P. And this B raised to the power P minus 1 by 2 using Euler's criteria is congruent to the Ligander symbol B upon P, and it is modulo P. Now, this is either 1 or minus 1. Similarly, the right hand side is also either 1 or minus 1. So both the sides are either 1 or minus 1. Now it comes to our mind, can it be that one side is 1 and other is minus 1? No, it is not possible. Because if one of the sides is 1 and the other is minus 1, then 1 is congruent to minus 1 modulo P will give you that P divides 2, and it is a contradiction because P is an odd prime. So either both are 1 or both are minus 1. So in either case, either both sides are 1 or both sides are minus 1, they are equal. So this means the Ligander symbol AB upon P is equal to the Ligander symbol A by P into the Ligander symbol B upon P. So this is the first result we proved. Then the second result for Ligander symbol, which is of the same kind, says that secondly, if A is congruent to B modulo P, then Ligander symbol A upon P is the same as the Ligander symbol B upon P. So A is congruent to B modulo P is given. A is congruent to B modulo P is given. Raise both sides of this congruence equation to the power P minus 1 by 2. So A raised to the power P minus 1 by 2 is congruent to B raised to the power P minus 1 by 2. But modulo P, this A raised to the power P minus 1 by 2 is congruent to A by P Ligander symbol. And similarly, modulo P, this right hand side B raised to the power P minus 1 by 2 is congruent to the Ligander symbol B upon P. So they are congruent to each other modulo P. Once again, it can assume values 1 or minus 1. It can also assume values 1 or minus 1. So either both will be 1 or both will be minus 1, because of the same reason that we have seen the previous result. Because if this is 1 and the other is minus 1 modulo P, then P will divide 2 and this will be a contradiction. So that means either both are 1 or both are minus 1. In either of the case, they will be equal. If it is 1, it is also equal to 1, then they will be equal. And if they are both minus 1, then also they will be equal. So if A is congruent to B modulo P, then Ligander symbol A upon P is equal to the Ligander symbol B upon P is the second important result of regarding Ligander symbols. The third one says that, third one is in fact a corollary, you can say. It says that A square upon P Ligander symbol is equal to 1. So this is very easy. We can write A square upon P Ligander symbol as A into A by P Ligander symbol, and by using the first result that we have proved in this video, we can write it as Ligander symbol A by P into Ligander symbol A by P or you can say Ligander symbol A by P square. Now this A by P Ligander symbol is either 1 or minus 1, so it is plus minus 1 square, and plus minus 1 square is 1, so A square by P Ligander symbol is always equal to 1. That means, for example, you have 4 upon 11, this Ligander symbol is 1, because 4 is 2 square. And that means, the beauty is here, this means that 4 is a quadratic, 4 is a quadratic residue of 11. Similarly, 9 is a quadratic residue of 11, because 9 is also a perfect square. So if you are trying to find the quadratic residues of a particular number p, then from the reduced residue set modulo p, all the perfect squares will definitely be the quadratic residues modulo p. It is being told by this result. And now we are moving on to another useful result of Ligander symbol, and it's again very easy. It says that the Ligander symbol A square B upon P is equal to the Ligander symbol B upon P. And once again it is very easy, because A square B upon P Ligander symbol, by using the first result that we have proved in this video, it can be broken into two parts, A square upon P Ligander symbol into B upon P Ligander symbol, and from the third part that we just proved now, this A square upon P Ligander symbol is equal to 1, so 1 into the Ligander symbol B upon P, so it is equal to the Ligander symbol B upon P. So A square B by P Ligander symbol is equal to the Ligander symbol B by P. Another important result regarding this is that 1 upon P Ligander symbol is always 1. There are many ways to prove this. One is that you can write that it is 1 square. So A square by P, you know that it is 1. So it is one way. Another way is by using the Euler's criterion, we know that A upon P Ligander symbol is equal to A raised to the power P minus 1 by 2. But 1 raised to the power anything is 1. So once again it is equal to 1. So it can be proved in several ways. And the last useful result regarding this is that minus 1 upon P Ligander symbol is equal to minus 1 raised to the power P minus 1 by 2, and that can directly be followed using the Euler's criteria. Just replaced A by 1, so A by P Ligander symbol is equal to A raised to the power P minus 1 by 2. In fact, by using Euler's criteria, it is congruent to this modulo P. But the same question arises again. The value of the left hand side is 1, 1 or minus 1. The value of the right hand side is also 1 or minus 1. Either they are both 1 or they are both minus 1, because if one of the sides is 1 and the other side is minus 1, then 1 is congruent to minus 1 modulo P will give you P divides 2, which is a contradiction because P is an odd prime. So either both are 1 or both are equal, and in both the cases they are equal. So minus 1 by P Ligander symbol is equal to minus 1 raised to the power P minus 1 by 2. So these are some basic results. So for example, if you are having a bigger number, say 43, and you want to see 24 over 43 Ligander symbol, what it is. So if I say you that using Euler's criteria, it is 24 raised to the power 43 minus 1 by 2, 21 modulo 43, it will take a long time, because it's not so easy to simplify it. But using the properties that we have just done, it can be solved in a short time using shortcut methods. So you can write it as 2 square into 6, 43, like this. Now A square B upon P. So A square B upon P is B upon P, so it is 6 upon 43. Further, 6 upon 43 can be written as 2 upon 43 into 3 upon 43. Now, 2 upon 43. It is congruent to 2 raised to the power 43 minus 1 by 2. Now 21, it is now easy. 21 into 3 raised to the power, similarly 21 modulo 43. And now it can be very easily solved in simple steps using that 2 raised to the power, suppose 6 and power 3 into 2 cube. Similarly, here you can have 3 power 3 power 4. You can take 3 power 4 power 5 into 3 modulo 43, just to simplify. 2 power 6 is 64, and 64 when divided by 43 will give you the remainder 21. So this portion will be 21 cube. And 2 cube is simply 8. So you can have 8 here. Now 3 power 4 is 81, and 81 modulo 43 is congruent to minus 5. So it is minus 5 here you can have into 3. Now once again it can be simplified. 21 square into 21, suppose 21 square into 21 into 8 into minus 5 into 5 power 4. 5 power 4 you can say 25 square, 625 into 3. Now once again this 21 square is 441. 441 modulo 43 is 11. So this portion becomes 11. 11 into 8, it is 88. And 88 divided by 43 will give you the remainder 2. So this product can be replaced by 2. Now 2 into 21, it is 42. 42 modulo 43 will become minus 1. So this product will be minus 1. And minus 1 into minus 5 is 5. So now you are having 5 into 6, 25 into 3. So it is 5 into 3 is 15 into. Now 625. If you divide this 625 by 43, you will get as remainder. 4217. So you'll get 23. So you'll get 23 here modulo 43, and it can further be now simplified. 23 into 15, it is I think 345. Yes, it is 345. And now the final division, 345 divided by 43. So I think it will get multiplied by 8. So 8 into 3, 24, 2, 3, 4, and you will get minus 1. So it is congruent to minus 1 modulo 43. So that means 24 upon 43, Ligander symbol comes out to be minus 1. But from here, if you directly try to solve it by using 24 raised to the power 21, it will take too much time. So it is a shortcut method, you can say, to find the values of the Ligander symbol of larger values, which can be simplified, which can be broken into the small factors. And now we are going on to prove another important theorem, that is Gauss lemma. Gauss lemma. So what the statement of the Gauss lemma is, let us see first. Let P be an odd prime. Let P be an odd prime. Let A be an integer such that GCD of A and P is 1. Now let N be the numbers of those least positive remainders which we obtain when we divide A, 2A, 3 and so on to P minus 1 by 2A by P. So let N be the number of least positive remainders or residues of A, 2A, 3A and so on, P minus 1 by 2A, which are greater than P by 2, which are greater than P by 2, then the value of the Ligander symbol A upon P is equal to minus 1 raised to the power n. So first let us prove this theorem, and then we will have an application of this theorem to find the value of some Ligander symbol A by P. But first we will prove the theorem. What we want to say actually, you are having a prime, odd prime number P, you are having an integer A with GCD of A and P is 1, that means A and P are co-prime to each other. Then you consider this set A, 2A, 3 and so on, P minus 1 by 2A. Divide each number of this set by P and look at the remainder and count the number of remainders that are greater than P by 2. Let it be n. Then the Ligander symbol A by P will be equal to minus 1 raised to the power n. This is the statement of the theorem. And now we move on to the proof. First of all, look into this set A, 2A, 3A up to P minus 1 by 2A. No two members of this set are congruent to each other modulo P. Because if, suppose, some IA is congruent to some JA modulo P, suppose if, then P divides I minus J times A. But GCD of P and A is 1, so P must divide I minus J. And this is not possible, this is a contradiction, because I and J are both greater than or equal to 1 but less than or equal to P minus 1 by 2. So their difference must also be less than P minus 1 by 2. And P cannot divide a number which is less than P minus 1 by 2. So this is a contradiction. That means no two members of this set are congruent to each other. This is the first thing, that no two members of this set are congruent to each other. Now divide these P minus 1 by 2 numbers by P, and definitely you will have some remainders. Some of the remainders will be less than P by 2, some of the remainders will be greater than P by 2. So separate them in two sets. So let A be the set alpha 1, alpha 2 and so on alpha m. These are those remainders which are obtained by dividing these numbers by P, and the remainder is less than P by 2 here. So these are such that these alpha i's are less than P by 2 and definitely greater than 0, because none of these numbers is divisible by P. Similarly, B is beta 1, beta 2, and I am writing here beta n, because n is the number of the positive remainders which are greater than P by 2. So these are the remainders obtained by dividing these numbers by P which are greater than P by 2. So each of these beta i's are less than P but greater than P by 2. Okay. Now consider another set C. Subtract each of these from P. So what the set you are going to obtain is P minus beta 1, P minus beta 2 and so on, P minus beta n. And now see what will happen to these P minus beta j's or P minus beta i's. Multiply this by minus 1, the sign of inequality will be changed. It will become greater than by multiply by minus P. And now add P to this. So P here and P here. Rewrite it starting from here. So P minus P is 0. So first write down 0 is less than P minus beta i's is less than P minus P by 2 is P by 2. Okay, so I'm rubbing this line now from here. Another thing now to be noted, these m remainders and these n remainders, they are all obtained by dividing this set of numbers by p. And how many numbers you are having here? P minus 1 by 2. So the total number of remainders must also be p minus 1 by 2. How many remainders are there? M. How many remainders are here? N. So this m plus n must be equal to p minus 1 by 2. Another thing, if you look at A and C, no member of A is equal to some member of C, because if some alpha I is equal to some p minus beta j, then alpha I plus beta j is equal to p, which is not possible, because the sum of two remainders, one is less than p by 2, another is greater than p by 2, their sum cannot be equal to p. So this is not possible. That means all the members of the set A and C, they are distinct. So take their union, A union C. A union C means alpha 1, alpha 2 and so on, alpha m, then p minus beta 1, p minus beta 2 and so on, p minus beta n. Now these are the remainders. Note that these remainders are nothing but actually 1, 2, 3 and so on up to p minus 1 by 2. You have divided p minus 1 by 2 numbers by p and you have obtained the remainders. How many remainders you have obtained? P minus 1 by 2. How many numbers are here? P minus 1 by 2. No two are same. Then that means these two sets are same. They are the same sets. That means the product of this A union C, and let this be the set M. The product of the members of the set A union C is same as, or you can say is congruent to, the product of the members of the set M. That means I'm going to rub the portion here because I'll need space now to write more. Now their products are congruent to each other. So this product 1 into 2 into 3 into up to p minus 1 by 2 is congruent to the product alpha 1, alpha 2 and so on, alpha m, and then p minus beta 1 and so on, p minus beta n modulo p. And we know that if we are working with modulo p, then any multiple of p can be removed. So remove this multiple of p, that is p, remove them. So what you are going to get is congruent to alpha 1, alpha 2, alpha m, then into beta 1, beta 2 and beta n. But how many minus 1s are there now? You are having minus 1 here, you are having minus 1 here, n times. So it is minus 1 raised to the power n. It is minus 1 raised to the power n here. Now these numbers, look at these numbers, alpha 1, alpha 2, alpha m, beta 1, beta 2, beta n. These are the remainders obtained when you have divided the numbers a, 2a, 3a, 4a and so on up to p minus 1 by 2a by p. So each of these numbers is congruent to some of the numbers from the set a, 2a, 3a up to p minus 1 by 2a modulo p. So you can write it as congruent to minus 1 raised to the power n, and in some order write here modulo p, and in some order these numbers are congruent to a, 2a, 3a and so on, p minus 1 by 2a modulo p, in some order. What the order is, we don't know, but in some order it will be. Once again, your left hand side is p minus 1 by 2 factorial is congruent to minus 1 raised to the power n. This a into a into a into a, p minus 1 by 2 times, it is a raised to the power p minus 1 by 2. And this 1 into 2 into 3 into p minus 1 by 2 is p minus 1 by 2 factorial modulo p. Once again, note that GCD of p minus 1 by 2 factorial and p is 1, because no factor of p minus 1 by 2 factorial is divisible by or divides p. So from here, this p minus 1 by 2 can be taken out and can be removed. So or you can say that they can be cancelled. Cancelling them, you will get 1 here on the left hand side, and this will be cancelled. And now multiply this congruence both sides by minus 1 raised to the power n. So it will become minus 1 raised to the power n, and here you will get minus 1 raised to the power 2n, and minus 1 raised to the power even is 1. So this is also equal to 1. Now this a raised to the power p minus 2 is equal to a by p, Ligander symbol. So minus 1 raised to the power n is congruent to a by p, Ligander symbol, modulo p. Once again, it can assume values 1 or minus 1. The Ligander symbol on the other side, a by p, it can also assume the values 1 or minus 1. Here you can have either 1 or minus 1. Here also you can have 1 or minus 1. So both will be either 1 or both will be minus 1, because if one of them is 1 and the other one is minus 1, then once again we will get that p divides 2, where p is not prime and it is not possible. So they must be equal, either both are 1 or both are minus 1. So you can say that the Ligander symbol a by p is equal to minus 1 raised to the power n, where n is the number of remainders obtained by dividing a, 2a, 3 and so on to p minus 1 by 2a, dividing by p which are greater than p by 2. So we have proved the Gauss lemma, and let us see an application of that. So suppose we are to find the value of 5 by 11 Ligander symbol. We have to find the value of the Ligander symbol 5 by 5 by 11. So here your a is 5 and your p is 11. First look at the set a, 2a, 3a up to and so on, p minus 1 by 2a. What is p minus 1 by 2? P is 11, so it is 11 minus 1 by 2. 11 minus 1 by 2 means 5. So this set will contain numbers up to a, 2a, 3a, a, 2a, 3a, 4a and 5a. This is the set now. And what is your a? A is 5. So what the set will become? 5, 10, 15, 20 and 25. Divide each of the numbers in this set by 11 and look at the remainder, what the remainder you are going to obtain. If you will divide 5 by 11, the remainder will be 5. If you will divide 10 by 11, the remainder will be 10. If you will divide 15 by 11, the remainder will be 4. If you divide 20 by 11, the remainder obtained will be 9. And if you divide 25 by 11, the remainder obtained will be 3. Now look at what is your p by 2. 11 by 2 means 5.5. How many of these are greater than 5.5? 1 and 2. So your n is equal to 2. Therefore, this Ligander symbol 5 upon 11 is equal to minus 1 raised to the power 2 is equal to 1. Or you can say that 5 is a quadratic residue modulo 11. So this is a simple application of Gauss lemma. So I'm going to end this video here. In the next video we will have more and more about the Ligander symbols. Till then, thank you once again.